Hello everyone. Today we'll solve problem number 42, implement a rectified linear unit ReLU activation function. And in case you're wondering, yes, this sweatshirt or hoodie that I'm wearing is from DeepML. If you go over here in the website, click on merch, you'll be taken to this website, which you can see all the cool merch that they have, mugs, shirts, hoodies, and sweatshirts. I got this one and I highly recommend it. I'm not getting paid for this, by the way, so I'm just recommending it because of how much I like it. This sweatshirt is comfy and it's warm. So it's great for this winter that's to come. There's still a promotion available for the first, I think, 100 units. So you're still on time in case you want to grab one of these and look comfy while you're solving all of the problems on deepml.com. So with that out of the way, let's dive into the problem. What we're going to do is we're going to write code for this ReLU activation function. Now, there's a wealth of knowledge out there about activation functions and ReLU and its cousin leaky ReLU, which we're going to cover in the next video. So I'm not going to spend too much time talking about the intricacies between underneath this model. I'm just going to give you the TLDR, what it is that you have to know, why it is that we're working with this function, and why they are relevant. So the ReLU function is simply this. It's just you give it an input, in this case, C, and you get the maximum out of 0 and C. So if you were to plot it out in a graph, you would see that, let me change the color, you would see that all of the values that are negative, that is to the left of the y-axis, are going to be mapped to 0. And then all of the other ones are going to be the same one. There's going to be the same value. So this function, although it's made by two lines, is a nonlinear function in the sense that, you know, if you were comparing it with all of the actual values here, like the red line is going to be the actual values of x, this would be the right relationship, but all of them are just being pushed forward over here. So that's all. That's the function. It's very simple, kind of intuitive. Now, you may be wondering, why is this relevant? Or rather, what does this have to do with machine learning and all of that? So let me tell you a little bit about when this is being used and why it's relevant. So if you think about it, if you've analyzed neural networks, there's sometimes have this, they most of the time have a structure like this. So this is going to be your input. I'm just going to call it input. And then your input is going to be transformed through a lot of layers. All of these squares are going to represent layers. You can have multiple if you have a very deep network. And then eventually you're going to get here and it's going to spit out a result. This is going to be your output. So the main idea of all of these layers that are in between is that you're going to introduce certain non-linearities within the model. And what I mean by that is, let's go back to what we were talking about in previous videos when we introduced linear regression. So the main idea of linear regression is that if you have your data like this, you know, a lot of data like that, then linear regression would be the best line that fits all of this data. But sometimes the whole pattern, sometimes the whole pattern of the data, like you can draw a line between this kind of pattern that I'm going to draw here, but the main relationship between independent and dependent variables is going to be nonlinear, right? So let's say, for example, this was the best fit, the line that fit the best. You can see that it's still not a very good fit. Like you can't do that much with this just by looking at linear models. Neural networks have this property that they allow you to uncover non-linear patterns. So this green line that I'm drawing right here would be a better fit through using a neural network. But how do neural networks do that? Well, the way they do it is by having these things called activation functions and within the hidden layers that grab the input that you have and then it passes into a function that introduces a nonlinearity on it. And what I mean by that is that if you didn't have this kind of function, then this whole neural network would just collapse into being something similar to linear regression, in which you would only have linear passes between things. By introducing nonlinearities, what you do is you force the data to behave in a different way, and that can fit this kind of pattern better. Now, I'm just giving you a very, very high level approach to this. As I said before, there's a lot of resources out there that can go into deeper detail. I want to give you the idea of why we need some nonlinear functions. So with that out of the way, if we think about it, the ReLU function, the one that I just talked about, the one I'm going to drawing right here, which could be something like this, is a fantastic nonlinear function in the sense that, it's very simple, but it still introduces a nonlinearity. So it may not be able to fully capture the phenomenon that we're looking here in this graph, but it will do a great work towards, it will do a great job towards approximating it. So ReLU, you can think about ReLU as perhaps the most simple of the nonlinear functions that you're going to use. And that's why it's so important to know and to code it up. Now, one last thing. So you may be thinking, okay, so this is great. It's a very simple function, right? ReLU, which is simply the maximum of 0 on the input. So what's the drawback? Well, as I said, it's so simple that it may not be able to fit all these patterns correctly, but it also suffers from another problem, which is called the dying ReLU problem, I think it's called. So what this means is that, let's say in your input and your intermediate layers, you're going to have a lot of negative values. What ReLU is going to do is it's going to kill all of them, right? So let's say if you were to look at the, let me clean this up. Let's say you had this pattern here and your real data behave like this. So you're looking at the negative values in X and you have something like this, a very intricate pattern right here in the left side of the axis. And then over here, you had something like this, on the positive side. If you use a ReLU function, what it's going to do is it's just going to squish all of these values here. So you're going to lose a lot of the information. Right? This whole behavior that you have here is just going to be destroyed by ReLU. So you will be losing a lot of information and your fit may not be as good because, as I said, you're just forcing all of this side to compress. So that's the main drawback of ReLU, and Liquid ReLU, which we're going to see in the next video, is going to take care of part of that. So now with that out of the way, let's write our code. So the only thing we're going to do is we're going to take the maximum between 0 and C, and we're going to return that. And that's it. All 3 cases are accepted. So as you can see, coding it up is very simple, but the main idea behind it is what I think is worth learning. As I said before, take some time to read some other resources if you want to dive deeper into it. I just gave you a brief overview of what's happening, but ReLU is something that you may use in your first projects. ReLU by itself may not be used a lot in production, but Liquid ReLU sometimes gets used, and that's the one we're going to tackle in the next video. See you then.